So hi everyone, welcome to our PhD seminar. And this week we'll have Professor Mariya here to talk about her study recently on how to analyze the intensity of longitudinal data collected with mobile phones. So let's welcome her.
Thank you. Thank you. I would like to have a sense of the background of people here, just to know how much statistical background you have and also how much background in technology and applications, and maybe a little bit of the discipline that you're in. If you can just shout out. What is it? Psychology, personal health informatics, I assume, right? Psychology and statistical. What is the background in statistics? Right. So some statistics. Okay. Okay. So the idea is that I won't go necessarily into the nitty-gritty of the statistical modeling, but what I would like to do is to talk a little bit conceptually about the advantages, some challenges, and also some of the opportunities that arise from collecting intensive longitudinal data. And my applications are in the area of psychology. I will be presenting two examples. One is from cancer patients, and they're dealing with pain. And the second example is smoking urges. So those applications in psychology, but the common theme is to think about research questions a little bit differently, and also think about how the multitude of data that we're able to gather with technology, how that can inform us to think of new research questions and also advance the research in maybe ways that we do not necessarily expect. So I would like to acknowledge the collaborators, and some of them are specifically provided data or helped me with developing the methodology for this talk. And part of this project was also supported by the NCI, and you'll see which part that is. So let me dive into this part of the talk. And traditionally, the way we think about people as being somewhat static. So if you think about questionnaires in psychology, we give people questionnaires, and then we may ask them if we're assessing, let's say, their depression or anxiety in the past 30 days or in the past week, how many days you've experienced this type of symptoms. So the idea, while this is the type of assessment that has been given in the past, if you step back from it, think about the conceptual kind of underlining of this measurement approach. The idea is that with one shot, we are able to kind of get a good idea of psychological experiences or psychological, phenomena that we're interested in, whether it's depression or anxiety or addiction, whatever it is that we're interested in. So it's one-shot deal, right? And what we're learning now, and I'm not sure that people maybe thought about it prior to developing a technology, or maybe the technology informed it about the way that people are, but very frequently you'll notice that we are dynamic. We are really dynamic human beings. So while I may have negative mood on Monday morning at 9 a.m. because maybe I did not sleep very well, Sunday to Monday morning, but then something happens and my mood shifts. And then as the week progresses, there are weekly cycles. There may also be daily cycles, physiological cycles, life cycles. So the idea is that not only people change, they may change in response to internal processes happening maybe systematically or not systematically. They also change and response to the environment. So this is kind of a process-oriented paradigm in psychology, and that's the shift that we're observing now as we're collecting data more longitudinally, and this longitudinal aspects, it becomes a little bit more narrow, and we're zooming in into people's behaviors. So what we're seeing is the observation of change on a somewhat micro scale, longitudinal micro scale. And this is possible by being able to use technology, right? So those of you who are in PHI, you know very well that technology can be used kind of as an ambulatory physiology measure, but it's in psychology we frequently ask people to respond and see how they're doing. So you might have seen this clip before, but I think it's just a strong point to kind of talk about this framework that we're in. So this is a person, you know, a little bit probably not very happy looking, so he carries a cell phone with him, and then in real time we can assess his health. We can assess emotions, feelings, kind of internal evaluative experiences. We can access physiology in real time. Cognition, so kind of a whole spectrum of experiences on a human level. We also know now with GPS systems where the person is, so we're capturing both internal and external environment. So because this is interdisciplinary type of research, so there are things that we're interested from the purely kind of perspective of, okay, what's the psychological process behind it? But now there's another step that makes this research a little bit more complicated, and that's the amount of data that we're acquiring from this type of assessments. Because if you think about it, every person may have hundreds or even thousands of data points. If we're doing this over time, several times a day, so there's all this data transmission that's happening in real time, and then we need to model this somehow to be able to inform this loop back to maybe intervention or prevention or explanation. So this is the intervention in this case. So from this whole cycle that we just observed, I'm going to zoom in onto the data cycle, and because that's what my talk is about, right? So intensive longitudinal data are typically the data that are collected over time, and sometimes you might have heard the term time series data. From the statistical standpoint, there are specific characteristics why time series data is a little bit different from intensive longitudinal data, and I'll talk about those in a little bit. So we have frequent sampling, naturalistic environment, that's what, we're capturing things in the moment, and we're focusing on momentary experiences, and there are a variety of applications of this. So from statistical standpoint, why these data are unique is because we have unbalanced design, sampling design. And sampling simply means that one person may be assessed 500 times, another person may be assessed 200 times, and another person, due to malfunctioning in the cell phone, whatever, may only have 50 data points. So it's unbalanced across people. It's also unbalanced within an individual because sometimes depending on the regimen of the assessment, we can have kind of bursts within a day. So it's not equal spacing of observation that frequently is a necessity for statistical modeling for specific type of models. But we have kind of unequal spacing. More information here, less information there. We have data missingness for a variety of reasons. And we also deal with large volumes of data. So this is the part that I think, this is maybe the most important part for you, and especially if for those of you who come to this talk from the applied standpoint. And the importance of this is what type of research questions can I ask? Because the research questions are a little bit different. So in traditional settings, we might be interested in kind of pre-post type of questions or cross-sectionally just describing the process. But here, we really look at people over time, and we zoom in into their behavior and the environment. So we have a bunch of different things assessing together. So the type of questions can be quite different. So, and I just wrote out a few examples of how they could be different, but there are clearly more. So does the effect of the intervention, let's say, change over time, and in which way? Is the effect of a covariate, time constant, or time varying? Is there a pattern of this relationship? So if we're looking at the relationship between X and Y, is it a constant effect, or is it a varying in time effect? Or maybe there are also group differences in this time varying effect. So the highlight here is that we're really incorporating the time metric here. So notice that there's change over time, and the time is a little bit more intricate, defined, right? And then is it time constant? Is it time varying? So we're really talking about dynamics. What's happening is all about change, and can we explain this change? So I'll talk about two scenarios today and two different type of models. And this is the first one. So say I have intensive longitudinal data from a single individual here, and I'm assessing that person's negative affect and smoking urges over a standardized period of time. So you can see quite a bit of fluctuation, and I'm just, for the sake of this exercise, I'm going to split the time interval into 3 sections. Right? This is where the vertical markers are. If I were to just simply correlate all the data to see if there is relationship between negative affect and smoking urges, so that when people are sadder, unhappier, angrier, maybe they're more likely to want to smoke, what I'm seeing maybe is absence of any relationship. Now, if I am actually going to look at the same data in the chunks of time, in these little 3 chunks of time, maybe this is the reality of the relationship that is happening. So it's positive in one part of life, it's negative in the other part of life, and maybe it's absent in the 3rd section of this observational period. So when I condense all the data, I lose that precision, right? And then when I chunk the data, and this is just a theoretical exercise, but that's what might be the case. Now, how do I know where to chunk? That's a problem, right? Because I don't know where those intervals are. So maybe in reality, I don't need to know. Maybe I can just look at those little sections continuously and then just get this relationship as a curve, right? So continuously looking at this correlation between the 2 variables and then seeing how the relationship changes over time continuously.
But if you have smaller time periods, then you will have fewer data points too. No?
Right. There will be fewer data points, but what I'm working with here is going to be, I'm working on a sample level. I'm not working on the individual level here. So I'm making use of data from different people, and this is going to be a very important point later on, just to think about how time needs to have a meaning. Right? So maybe it's a smoking cessation process. Maybe it's stress level prior to a major examination, and then how that changes with time. Maybe it's a physiological process, and time is just a proxy. So it doesn't have to be time. It can be something else that is meaningful. So, and now I'm translating that into a model. But that's the motivation behind this first statistical model that I'm talking about today, and that's the time varying effects model. So notice I don't have to go into the specific details around the model, but I'm going to just highlight some things. So if you ignore the parentheses, right, the TIJ in parentheses, maybe some of you recognize this model. You have y as an outcome. You have beta 0 plus beta 1 times, let's say, tx is a treatment. You're looking at the effect of a treatment on some sort of an outcome. So it's a regression model, right? It's a simple regression model where you look at the effectiveness of a treatment. Now, what differentiates this model from a simple regression model is that you have those functions both for the intercept and for the slope now. So it's not one number that we are estimating, but we're estimating a curve over a specified period of time. And in this case, beta 0, the intercept, is the trajectory for, let's say, a group that did not get a treatment, if we're thinking of treatment as a binary variable, yes or no. And then beta 1 is the effect of treatment at a particular time. So everything is linked back to time, right? Because remember, we are now focusing on time or whatever underlying process is going on there. So both intercept and slope are time specific, and they're also dependent on time. Their magnitude depends on time. So this may be a visual analog of what we're looking at. So let's say that this is a control group, and the effect is somewhat lower here, right? And then you can see that the effect of the intervention is not the same. It's varying depending on what day in the study we're talking about, and if the outcome is quality of life, let's say. Okay? So this is the statistical framework. Now, there is a specific macro that has been developed, so there is a way to apply this type of modeling, right? It's not just kind of theoretical, but there is a SAS macro that can be downloaded from the Methodology Center website. And I didn't go necessarily into the specifics of the estimation process of how this is estimated, but there is accompanying kind of manuals and literature that go with this. These models can also be applied to different type of outcomes, continuous binary count, so there is some flexibility. So let me now share with you an example of how this can be applied. This data comes from a study with cancer patients. So there were 59, almost 60 lung cancer patients, all of them with early stage of lung cancer. So they were kind of standard in their level of disease. They went through 2 surgical procedures. One is more standard. I can go into some details, but it involves spreading of the ribs and really going for the lungs with open rib surgery. And the second involves video-guided, a more advanced type of a surgery. So the idea was to see if one surgery maybe has a different impact on how patients recover versus how they recover from a different type of procedure. So this was the overall goal of the study, and we're going into the kind of the psychological part of it. So patients were given this device, and that's why the study is called Lucy, because that was the name of this device, Lucy. So it was an accompanying friend that kind of followed their recovery process for 2 weeks, and they were filling out assessments twice a day for 2 weeks. And so you can see the compliance rate. On average, they provided about 16 assessments. Median is 18, and there's quite a bit of spread, right, from 3 assessments to 28. And we're focusing on their symptoms, physical symptoms. And this is the list of them. So we're looking at pain, lack of energy, drowsiness, lack of appetite, constipation, shortness of breath, coughing, and chest tightness. So all of those have been shown that lung cancer patients really suffer from this particular type of symptoms. So the scale goes from 0 to 8. It's a count symptom, whether that particular symptom is present or not. And you can see that on average, the mean is like 2.5. So they have at least 2 to 3 symptoms on average. So these are the raw data, just randomly selecting 10 people from each group. VATS is the advanced procedure and thoracotomy is the standard procedure, it's a little bit difficult to make sense of this, they're called spaghetti plots. So it's really difficult to see what's happening necessarily here. You can see missing data here and there, so you can see those, I mean, those challenges of intensive longitudinal data.
How are you scoring the data from responses like sample lot maybe in the demonstration that you had?
So yes, no.
Oh, some of them were sample lot scale.
So, right, it's a sum. It's a sum if the symptom is present or not on a given moment.
Right. So if they said something.
So the checklist, let's say they have a checklist. Say, do you have the symptom? Check all symptoms that you're experiencing right now.
These aren't the questions that had the different categorical responses.
In the previous slide on the monitor, there were categorical, like some, none.
Oh, I see. Right. So it was a two-part question, right? And it was a not normal distribution. So we kind of, contemplated about how to analyze the data. So there is information about the severity of the symptom, but for these purposes, we're just looking at whether it's present or not. So we kind of, simplify the exercise. Yeah, but it's a good question because you want to know what the outcome is. So you see that the scale goes from 0 to 8, so that's the number of symptoms. And it's visually difficult to say, but it seems that maybe in this group there's a little bit less going on, but it's difficult to assess that. So first, we took a shot at this with standard multi-level modeling procedures. Sometimes it's also called mixed effects modeling, hierarchical modeling. So, and it's a parametric type of approach. So the finding is, after smoothing those curves, there is quite a bit of fluctuation in terms of the inter-individual differences. You can see individual lines and then the estimated average, blue. But essentially, we found no group differences here. And we found a general quadratic kind of decrease in the number of symptoms. So improvement, that's expected, and it seems that there were no group differences. Now, after this, then I feed this model, the time varying effects model, to see if there are group differences. If I actually look at the effect, not just kind of in a one slice shot, is there a baseline difference, or is there change in a linear slope and quadratic slope, but at each time point if there is a group difference between the two. So this is what I'm getting for the trajectory of the standard group, and this is the group difference for the modified surgery. So beta 1 in this case is the difference in the effect. Now 1 in this case, because this is a Poisson distribution, so it's a count data, 1 would mean no effect. And then so the average line, kind of, this is the thicker line here, and then we're looking at standard errors, the band of the standard errors around. So there's no effect up through day 4 or 5, and then we're seeing improvement in the VATS group, in the advanced surgery group. So when we're looking at them together, this is more of the, more clearly we're seeing where the effect is taking place. So it's not happening overall in the beginning. There are quite similar recovery types and shapes in the beginning, but then we're seeing somewhat a faster improvement in the other group after day 4 or 5.
So you have overlapping standard errors in the number of symptoms between the VATS and the Thorpe end of the data. Is that some weird curve?
This is just like they're called edge effects, because this is the way that this is estimated. The curves are estimated. They're kind of slicing the data and moving, right? So ideally, we would want to have more data here, maybe through day 16 or 18, so we would get more precision in estimating the end lines here. So then the error bars are really, it just tells me that there's not enough information to talk about the endpoints. So So this is the implication for this particular study, right? But I also maybe want you to think about, again, back to research questions, the effect of the treatment. We're unpacking it a little bit. We're not simply looking at the effect of the treatment on average, right? But we're really looking at the effect of the treatment over time and progression of that effect. And if the effect is present, what's the time interval for that effect? So that's kind of the zooming in that's happening here with this type of modeling. Okay, so, and moving on to the second scenario now. So imagine, again, we're going back to the data. We're looking at negative affect as the outcome. How angry are you right now on a scale from 0 to 10? And we're observing it for 14 days. Now we're dealing with smokers. And let's say that this is, again, just a single individual. We're seeing quite a bit of fluctuations up and down on a daily basis. And maybe what we want to do is to see if there's any relationship between this negative affect process, especially if for some reason this was an important time period. Let's say that this was negative affect assessed during an attempt for quitting cessation, right? So they quit on day 14, and then we want to see if that process of of negative emotions, if it predicts smoking status later on. So essentially, the problem here is that we have intensive observations on the predictor, on the X, and then we have a distal outcome that's assessed later in time, and it's assessed only once. So it's a scalar. It's one data point. And if you think about it, it's a challenge. It's quite a challenge. So you have, I don't know, 50 data points, let's say, on the predictor, and you're trying to make a prediction of the outcome. Let's say if it's a yes or no, number of cigarettes. So you can't fit them together in a simple regression model, right? You just can't do that. And we are talking about prediction. So the problem here is the mismatch in the scales between the independent variable and dependent variable. So of course there are ways around it. So there are ways that people try to kind of solve this problem, and there are several ways, right? So one, maybe you can take an average of this process, and then you can also talk about the variability, how volatile the negative affect is from moment to moment. So that may be one way. You can also look at the trend of negative affect, especially leading to a quit day, if it's increasing or decreasing, and then use individual model parameters, regression model parameters, as predictors of the outcome. Or maybe for some reason there is one time point that's the most prominent, and you think of using that data point or a few of those prominent data points as predictors. But again, the question is, how do I know, unless there is a very strong theory, how am I going to choose those data points? So all those approaches that I just discussed, they involve some sort of data reduction. So not only the data reduction, it's valuable. So it's valuable because we need to solve the problem. But what that data reduction also does, I think it's also changes the way we think a little bit about those intensive longitudinal data, because we are trying to condense the dynamics of what's happening into some sort of static summaries. So it's, it's a different way of thinking about and going from a lot of information to just condensed little information. And from the predictive purposes, it also has an impact, because if you're trying to predict something, once you condense it, you lose predictive power overall. And then sometimes we don't know what features to choose to make the best prediction. So, there's a specific reason of why I'm setting up, right, the problem, because of course then I'm going to say, okay, here's the solution for you. And this is the motivation for why this specific model was developed. And this model is also kind of, it incorporates time specifically. So functional regression. And first I'm writing in a regular regression model, right? Where you have, again, an intercept and a slope. And then the extension of that is the functional regression. And the functional regression unpacks that beta coefficient, that slope coefficient, and makes it into an integral. So what's happening now is that we're using that beta instead of single number, we're estimating it as a curve, right? And then looking at the whole area under the curve as a prediction information for the outcome. And I'll talk about this integration a little bit more in the next slide. But first, conceptually. We are not condensing the data, but we are trying to make use of a whole data structure. Now, this type of models, and this is important to know, that this type of models have been used. And they have been used mostly for physiological data or in engineering. Because the type of data that you get from, from physics or engineering context, it's continuous and clean data. But here, as we talked about, it's different type of data with different challenges and different features. So this is something that needs to be accounted for when applying these models. And this is the contribution that was done. So let me talk a little bit more about the integral here. So I'm just unpacking that beta coefficient. So if you think about it as a curve, right, that stretches from the first observation time point to the last observation time point. So we're looking at this time interval. Integration really is the area under the curve, right? So we're looking at the volume. And then with integration, it's always challenging. And maybe some of you can do a better job of explaining what we're trying to do if you've taken calculus recently. But I'm trying to simplify it, right? So it's easier to simplify the integration problem if you chunk this whole area under the curve into specific intervals. So we may want to chunk it into something that is, kind of small pieces of time. And then within each of those time intervals, there is a rectangle, right, that approximates the area under the curve. So we know geometrically how to compute volume, the area of a rectangle. We know that, right, just in 2 dimensions. So base times height, right? So, and if we do it for the whole curve, we can approximate the curve quite precisely if those time intervals are small. If we minimize the time intervals, that we can really approximate the area pretty well. So, and this is just formally writing this out, right? So we're looking at specific number of time intervals. We're estimating the area of this rectangle. And what's important for us here to know is that really base times height is, this is what we're writing here, right? These coefficients, the beta coefficients, are essentially becoming weights, right? So what we're really doing, we're kind of moving in time, and then the beta coefficient becomes the weight of the function at a given chunk of time. So in essence, what we're doing, we're saying, do I need to upweigh or downweigh this area of observation? Is this more important for prediction, or is it less important for prediction? So it's almost like, some of you might have worked with data that has weights, right? So you use it different ways for different people, depending, let's say, if it's stratified sampling or something like that. So that's what we're doing. We're essentially weighing different regions of the curve. Some of it may have more prediction, and some of it may have less prediction for the outcome. And that's that's essentially what the integration is doing. So in this case, the regression function is the population level on function, and it's not a single number. And it represents a series of weights for a specific predictor. And that weighing function emphasizes the regions of more importance and downplays, de-emphasizes regions of less importance. So again, there is a way to do this and apply it to intensive longitudinal data. And John Ziek at Penn State was a collaborator on this project. And he developed the R function for fitting this type of models. And it's a FunReg. We just played with different names for this, so let's call it FunReg, functional regression. And it's freely available for download as well. Different type of outcomes can be used for this type of models, different type of predictors. So let me just bring this home and go through an empirical example of how this can be applied and what type of questions you can answer with this type of modeling. So in this case, data came from a smoking cessation study. And there were two types of groups, the nicotine replacement group and just general cognitive therapy, cognitive behavioral therapy. So we have two treatment groups, and all individuals carried a cell phone or a Palm Pilot device, and they were assessed 2 weeks prior, their quit attempts, and 5 weeks following their quit attempts. So that's what we're zooming in, those 7 weeks of data. We also have number of smoked cigarettes as the outcome, and those were assessed 3 months after quitting. So that's essentially what we're interested in. And smoking urges are assessed in the morning. So I'll get to that. We have a sample of 300 people here, so it's quite a large sample size. You can see the breakdown by treatment. They're heavy smokers, smoking more than a pack at baseline. Look at the volume of data quite a bit, right? So we'll have 14,500 of data points just from the morning assessments. The mean about 50 per person. And we're looking at this variable. How much do you want to smoke right now on a scale from 1 to 11? So the mean is in the middle of the scale. And then the outcome is the number of cigarettes smoked. So it's a count outcome. How many cigarettes? Well, the good thing that the mean is lower, right? If you look at the baseline mean and the 3 months mean, it's lower. So it's encouraging. So this is the model. We're looking at the time interval minus 20 is the days. So we're looking at the days. 60 days altogether, minus 20 to 40. And we're looking at cravings in the morning. How that predicts the number of cigarettes measured 3 months later. So this is the marginal correlational plot function. And this is just slicing data into chunks of time and correlating predictor with the outcome. And you can see that the relationship between negative affect and smoking is not the same. So it changes over time, right? It's not a constant. And we're also seeing, I mean, that's quite expected, that recency effect is very strong. So the closer you are assessed to the outcome, the better the correlation is. Recency effect. Now, if we plug in this data into FunReg, this is the weighing function that we're getting, right? And this is a little bit challenging to interpret, but what's essential here to notice is that there, again, 0 is no effect, right? So wherever the function includes that 0, essentially it's not very important. The weight is close to 0. And then we're seeing positive and negative weights. So the period right before the quit attempt has more weight accounting for everything else, because this accounts for the whole data. And then the period, this is the recency effect that we observed here as well. So those two time periods, the most recent and the one that preceded the quit attempt, they seem to be the most prominent for predicting how many cigarettes somebody smokes later. So in this case, this is the nicotine replacement groups. Now let's take a look at the second group. This is a control. So in the control group, we're also seeing that increase over time. But let me go a step back. Here, we see the pattern is a little bit different there, right? The correlation function is a little bit different. And now, if we look at the Wayne function, it is also different here, right? So there is recency effect. And you can see that really the pre-quit negative affect didn't have that much of an impact for predicting the outcome. And this initial kind of what you came with into the study initially, kind of the naturalistic experience of negative affect before even going into quitting, that seemed to be more of playing a role for prediction. So we're looking at group differences here as a summary, right? We're looking at group differences. We're noticing those periods of time where things are more prominent, they have higher effect and higher impact for prediction. And we also can differentiate between those different processes that are underlying the data. In this case, the underlying process is the quit attempt. So because everybody quit on the same day. So let me wrap this whole thing up together, and again, bring us back to the discussion from intensive longitudinal data to how we can conceptualize the models, maybe the theoretical models, and how also statistical methods that we choose, they matter for what you find, and they also matter for how theories are built, right? Because I think what's happening very frequently is that when we dive into these new types of quite intense assessments, we frequently approach it from the knowledge that's already accumulated from traditional theories. And sometimes they hold and sometimes they don't hold. And we can also find something unless we give more flexibility, right? So if you go with your hammer, you will only do one thing, right? So if you only look at pre-post, that's what you find. But if you allow for a more nuanced examination and just even think a little bit out of the box in terms of the questions that you can ask, then maybe the answers are also will be different. And the way that we understand the behavior can also be different. Something that's quite important is the importance of time and the dynamics, right? The time, because these are group-based models, time is important because frequently it represents an underlying process. And what I want to also say that these are some of the tools, but these are not the only tools, right? So these are tools that are available for specific types of questions. And maybe there are other tools that are going to be better used for different type of questions. And here, the importance of time and the underlying process is important because you need to think conceptually what this means, especially since you pull in information from different individuals. You are able to discover interindividual differences if you are looking for them, like, for example, group differences, intervention differences, but there may be much more, right? And you can look for them. You can include covariates. You can model them. But that's, again, you can find an answer only if you're looking for it. So I think I'll stop here, and I'll see if you have any questions.
So within your data, if for a participant, some of the data points are missing, you have to remove that, or you still include that participant?
So for missing data, you don't need to have the same number of observations everybody's included. So even if a person has only one assessment point, you can still use that person's data in the estimation. I mean, it's not ideal, right? I mean, you have to figure out why would you include that person. But you don't need to have the same number of observations or missing data outside for the reasons of why it's missing. You can feed those models. Anything comes, yeah.
When you're getting the functional regression, so there's a time varying data definition. So do you have any restriction on the class of functions that the data belongs to? Because I saw like the nice number like splice.
Right, right.
I guess there should be trade-off between like the complexity of this function and the uncertainty about it.
Yes, yes. So we're making an assumption that there is a progressive smooth change. So it can be time varying, so it's not parametric, so it can change, but it changes, there is no breaking point, there's no jump, right? So it's a smooth, gradual transition. And I think for the psychological processes, it's probably a safe assumption, because if I'm thinking how my affect is going to affect if I want to smoke or not, I'm imagining how would it feel, but it's because I'm looking at the relationship between the two. While the affect is volatile and urges are volatile, I'm looking at the relationship. So the relationship is unlikely to just from the morning to the evening, it's unlikely to just completely switch. So the idea is that maybe they weaken, they change over time, but not drastically.
So we assume some continuity.
Yes, yes. Mm-hmm.
Can you translate this model to a logistic model?
With a binary outcome? Yes, yes, you can. So we can have continuous, count, and binary outcomes. So we can, instead of number of cigarettes, we can have if you smoke or you don't smoke. And actually, now it would be, I'm looking for applications and I'm looking for demonstrations to how to, to demonstrate this type of model. So, there are maybe possibilities for, let's say, developmental type of research to see how kids grow, right? Maybe some processes, developmental processes that are happening early on and during adolescence, and how that impacts some outcome later in life. Incarceration, how much money they're making, education completed.
You have data on dreaming, if the people have bad dreams on mobile.
Dreaming. Okay, yes. Yeah.
How much does the temporal quantization sort of impact the result? Does it matter? If you have this, so if you have sort of the same data, or is anybody looked at same data, but in one person it's measured, every 2 hours, the other person's measured every hour? Is that going to have an impact in what would happen here?
I think it's a kind of a two-question answer, because you can estimate it. So for the estimation, it can estimate it. It doesn't matter. The model would fit. So it's just that you have one person has, let's say, twice the amount of data than the other one.
Right.
But it's possible. So the good thing from this is that you can, let's say that the person who provided more data has maybe the same kind of underlying process that provided less frequent data. So you're able to estimate from everybody, right? And you are able to then, the person who provides more data informs kind of a more precise estimation for everybody. Now, for the purpose of kind of just, outside of statistics, kind of more conceptually speaking, maybe you're not capturing something important in those, time points that you're missing. From statistics, you can fit it. It's not a problem.
So if you took a data set here and you essentially subsampled off the original data set,
Mm-hmm.
do you statistically do you get, is there anything that sort of impacts the result there? If you end up with a situation where twice as much data, you're getting a different result.
Oh, okay, okay. So we did simulations on this, right? So we varied a couple of different parameters. So how many intensive assessments you're getting per person? So kind of the trade-off. Is it better to have more people or more assessments? That was the question behind the simulations. And the answer was, it's better to have more people than more assessments. So you get more information by having 300 people than 150, then having 150 assessed twice as much.
Okay.
Because it's, you know why? Because it's the outcome, really. Because what's happening is that you're looking at the distal outcome. And if you have distal outcome only from 150 people versus 300, you're estimating better from 300.
Okay. But in the first model,
yes,
you would prefer to have the distal
right. Right.
Probably it's because we can estimate each subject variances besides that the reading, so they have more error.
And especially for logistic regression, when it's a binary outcome for the second model, if you have, let's say you have only not that many people and not that many events, it's challenges. Like even for logistic regression, you need more sample, you need more people. So this is more complicated than logistic regression. So you still need a decent number of outcomes there. Yeah.
Do you have any methods for selecting the time points which you should optimize on the data point? Should you do it all at 7 a.m.? Or should you do it randomly, or are there ways of, during the experiment, to choose a point which, based on previous data collected so far, you should now test this person within the next 10 minutes or so, interrupt their day, because it would be more informative to find out how the progression was there.
Right. So I can repeat the question just for the audio, right? Right. Okay. So and then the question is about the timing of assessment, right? The optimizing the timing of assessment and thinking about, is it better to assess everybody at the same time points or stagger it? So for statistical modeling, it's better to stagger. So because we're essentially assuming an underlying process and we're pulling from people, pulling from everybody, so it's better to stagger. But outside of statistics, so that's the kind of just the statistical answer. But outside of statistics, I think it's also important for whatever is it that you're examining, right? It's more about the process that you are trying to capture. So there are some things, because we're really talking about ecological momentary assessments and different frameworks of sampling, and there have been developed several frameworks, like exactly having the same time window, like an hour basis, and then randomly within that hour, or maybe event-based or person-initiated, things like that. And that depends on the process. What is it that you're studying? So do you want it to be an unexpected kind of sampling of behavior? Or do you want it to be, tagged to a specific event or behavior? So there is never one answer. It frequently depends.
There are statistical tools you can use to maximize or minimize variance. There will be times where
Using previous data. So like online, adaptively.
definitely choosing.
So based on what you've collected thus far, when is the next best time to test it?
If you find that there's no variance after 3 tests at 7 a.m., then there's no point testing at 7 a.m., so the next test should be at a different time.
Right. 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 So there is, we talk about, so Neelam Ram, we published a paper in 2011 and in multivariate behavioral research, and talked about this concept of process speed. So like thinking about self-efficacy, for example, having a slower speed of change. So because self-efficacy towards quitting may be kind of pretty robust from moment to moment, maybe changes from day to day as you're going through the process and acquiring skills, but it's not going to change from moment to moment because it's pretty stable, right? And then emotions are being more volatile. So they can fluctuate, and there's like, you know, more precision into hour to hour, maybe your emotions, your negative affect changes. So I think it depends on the process. So there is no, again, no one answer for that fits all, because it depends on how much the process changes, like growth curve for kids, right? It's like really month to month or maybe a few months apart. But then, so it depends what the process is. And I think frequently it's a research question. We don't know. We don't know what the process is. So it's better to oversample and then go backwards and say, well, you only need to sample it really that many times. Yeah.
So I'm thinking of a sort of a different domain. Take an example, like if you were measuring whether or not somebody was hungry, and then the particular point in time, your measurement point was, did they eat?
Mm-hmm.
Right. So it's something for a given individual that would happen over and over and over again. So I'm imagining if you were measuring that, you know, sort of, are you hungry, and then are you hungry at a couple other factors, and then did you eat?
Mm-hmm.
And would this type of model apply in that situation where at the individual level you're going to get a number of those and an outcome, and then at some point you want to say now I can sort of predict what's going to happen for this individual in the future based on what I've seen in this number of examples?
I think it's better for this example to go with kind of person-based modeling, maybe time series, like states-based modeling, right? Because then you're really looking for causality there, and then especially with there is a challenge between the time intervals and how frequently you assess, but then it's really this assessment linked to the next, the following assessment linked to the next. So experience linked to behavior, right? And then those, I think, are better modeled with time series type of models. So it's a different question.
Is it really, I mean, but if each one of those things you treat it as sort of a separate example, as if it was sort of a different person, is it different than that? I'm not sure I understand why it would be different than that. I mean, there you have one trajectory per individual and an outcome. Mm-hmm. So if I then map that onto a single individual, a bunch of trajectories out, trajectory outcome, don't I end up with basically the same type of data?
You do, yes. So you're thinking of, if you have a trajectory like a predictor, right, that's intensively sampled, and then an outcome. Again, predictor and an outcome.
Yeah.
Yeah, I mean, it's something to, something to think about. Yes, thank you. Thank you.
Thank you.
Yeah, thank you.